Hey everyone, and welcome to this explainer. I am so incredibly pumped to have you here today. Look, if you've been skimming the tech news lately, you've definitely seen the buzzword quantum computing popping up literally everywhere. It sounds like straight up science fiction, right? Well, today, we're going to completely demystify this stuff. And I promise you, we are going to do it without getting bogged down in all that heavy, confusing jargon. By the time we wrap up, you'll have a crystal clear understanding of what quantum computing actually is, why it's such a massive deal, and exactly where the tech stands today.
So here's our roadmap to get us there. We've got 5 sections today. First up, not just a faster laptop. Second, the magic of qubits. Third, decades in the making. Fourth, welcome to the noisy era. And finally, number 5, the fault-tolerant future.
All right, let's dive right into section 1, not just a faster laptop.
I want to start by asking what is easily the most common question people have about this whole space. Is a quantum computer just a super fast laptop? Let me just stop you right there and firmly answer that absolutely not. It's so tempting to think of these machines as just, the next big processor upgrade for the computers we already use. But honestly, that completely misses the fundamental shift in how they actually operate. Think about it this way. Traditional classical computers process information using bits. Everything basically boils down to a rigid 0 or a 1. They're totally perfect for your everyday tasks, right? Browsing the web, word processing, running business software. But quantum computers, they use qubits. They aren't just faster versions of your MacBook. They are a fundamentally different tool, purpose-built to solve incredibly specific, wildly complex problems. Which brings us to section 2, the magic of qubits. Let's meet the real stars of our story. In regular classical computing, a bit has to decisively pick a side. It's either a 0 or a 1. But thanks to the weirdness of quantum mechanics, a qubit exists in what's called superposition. Basically, it represents a probability distribution over 0 and 1 simultaneously, right up until the exact moment you measure it. The main takeaway here? Instead of checking possibilities one by one, a quantum computer can explore a vastly larger space of solutions all at once. And qubits don't just fly solo. They can get deeply correlated with each other through this property called entanglement. When qubits are entangled, the state of one instantly influences the state of another, even if they're completely separated. It is wild. But it lets quantum computers process interconnected information in ways that classical, isolated bits simply can't pull off. The third piece of the puzzle is interference. You see, quantum algorithms are cleverly designed so that the wrong answers actually cancel each other out, while the correct answers reinforce each other. When you combine all three, superposition, entanglement, and interference, these machines don't just give you a tiny speed boost. For certain problems, they theoretically achieve exponential or quadratic speedups over classical approaches. It's a real game changer.
Okay, moving on to section 3, decades in the making. Because building a machine that can actually do all this didn't just happen overnight. If we trace this back to the 1980s and 90s, the theoretical groundwork was being laid by some legendary physicists, guys like Richard Feynman and David Deutsch. They essentially proposed that quantum systems could simulate physics in entirely new ways. After that, we got some major algorithmic breakthroughs in the mid-90s, and then finally, we started seeing actual experimental physical qubits pop up in the 2000s. I want to pause here for a second because 1994 was a massive turning point. A researcher named Peter Shor developed what's now famously known as Shor's algorithm. He proved mathematically that a quantum computer could factor large numbers exponentially faster than a classical machine. This specific discovery is what truly made everyone sit up and pay attention, mainly because factoring large numbers is the absolute bedrock of all modern global cryptography. Then, just 2 years later, in 1996, Love Grover developed a quantum search algorithm that offered a quadratic speedup for searching through unstructured databases. Just another huge milestone proving that, hey, if we can actually build these things, they're going to completely revolutionize how we process data.
By the 2000s, the race to build the hardware was officially on. Researchers were creating early experimental qubits using some really fascinating methods, things like trapped ions, superconducting circuits, and photons. But there was a massive catch. These early setups were limited to just a handful of physical qubits, and they were plagued by super short coherence times, meaning they'd lose their delicate quantum state incredibly fast, usually way before you could finish a complex calculation.
So, where are we right now? Let's get into section 4. Welcome to the noisy era. Well, the scale has definitely grown. Today, heavy hitters like IBM, Google, and IonQ boast quantum computers packing anywhere from hundreds to well over 1,000 qubits. That is a gigantic leap from the little handful of qubits we were playing with back in the early 2000s. But here's the reality check. We are currently living in what researchers call the NISQ era. That stands for Noisy Intermediate Scale Quantum. It's a crucial insider term to know. It basically means today's qubits are, well, noisy. They have high error rates, they lose coherence quickly, and because they're so fragile, you just can't run overly long or complex computations. Right now, these machines are mostly being used for research and algorithm development. They aren't outperforming classical computers on everyday business problems just yet. Now, you might be thinking, wait a minute, didn't Google claim quantum supremacy a few years back? And yes, they absolutely did in 2019. And later on, Chinese and other research groups made similar claims. They successfully showed quantum processors performing a specific task faster than classical supercomputers. It was an incredibly impressive proof of concept. But the context here is key. The task was highly contrived. When it comes down to practical, everyday use, we aren't quite at the point where we're solving real-world problems better than classical machines.
So what's the immediate goal? The absolute frontier right now is quantum error correction. Because individual physical qubits are so insanely fragile, the strategy is to group a whole bunch of them together to encode just one rock-solid logical qubit. Companies are laser-focused on stabilizing these logical qubits, and we're actually seeing some really exciting real-world progress on this front right now.
Which brings us to our final stop. Section 5, the fault-tolerant future.
Once we finally conquer error correction and can build large numbers of stable logical qubits, which, by the way, most experts estimate is still years away, we hit the era of fault-tolerant quantum computing. And the practical applications are going to be mind-blowing. We're talking drug discovery and materials science because quantum systems can easily simulate complex molecules. They'll tackle massive optimization problems across global logistics, finance, supply chains, and yep, they are going to completely upend cryptography. Just to be super clear, though, your classical computer isn't going anywhere. In the near term, progress is going to come from hybrid classical quantum systems. Think of it like a massive team-up. Quantum and classical supercomputers working side by side, each tackling the very specific parts of a complex problem that they are uniquely best at solving. But we really do need to talk about the ticking clock in the room. Remember Shor's algorithm? Because fault-tolerant quantum computers will eventually be able to shatter current encryption methods, there is a massive global push happening right now for post-quantum cryptography. Organizations like NIST are already racing to develop encryption standards that can actually resist quantum attacks. We have to figure this out today, years ahead of the actual threat. And that leads me to leave you with this final, kind of lingering thought. We know for sure that the quantum horizon is approaching fast. And we know this global push for quantum-resistant encryption is happening as we speak. But will our global digital infrastructure be ready in time? It's a huge real-world security question born from literally one of the most fascinating scientific frontiers of our lifetime. Thank you so much for joining me for this explainer, and hey, keep your eyes on the qubits.